So this is the video for three-phase testing. So when the tester switches on, it will come to this screen, resistance. What we have to do first is select the folder and record. I'm not sure if you heard all this, so I'm going to repeat it. So the active folder and record, mic and record 123, is where the data will be stored. If you want to change that location for storage, you press on the folder icon, and maybe you keep mic, but you want a new record, and maybe it's a different job number. So we can say now 987 job number. Okay, so now the active folder is still mic, but the active record is 987. Okay, so then we can make the first test, which is in sequence of the icons, is the low voltage, then megohm, then surge. So first, resistance. Okay, on the ZDS testers, you've got lots of options. So if you press this icon here, you get the choice of resistance, inductance, capacitance, single phase testing, and this is for RIC testing, rotor influence check or rotor bar check. I don't think either of you have that. So let's start with resistance. Okay, we can select copper or aluminium, and we can put the temperature in. To be honest, for winding resistance, there's no need to put temperature in unless they're a motor manufacturer. All we look for is balance between the three phase-to-phase readings. So we've got my motor, we've got the 3 Kelvin clips connected to the stator leads. And obviously you've got to make sure that both sides of the clip are well connected, as it's a Kelvin connection. So to run a resistance test now, you just literally press the test button and release. Okay, it says at the top of the screen, leads energized. Not sure how clear that is. And it's going to measure now between phase 1 and 2, 12.69 ohms. Now between 2 and 3, 12.68 ohms. And 3 and 1, 12.66. And then it will calculate the unbalance, percentage unbalance, 0.1. So that tells us that the stator winding is very balanced and our connections were good, made with the clips, and there's no loose connections or high resistance connections. Okay, so I'm going to connect my 3 phases, lead 1 to phase U, 2 to V, 3 to W. The leads are numbered 1, 2, 3, and they're colour-coded red, blue, yellow. Okay, so I've got my 3 connections. I've got my ground connection to the core of the stator. Before we run a megohm test, we need to ideally put in a temperature, because the temperature of the winding affects the megohm value greatly. So the higher the temperature, the lower the megohms. So what we want to do is measure the copper temperature with a handheld gun or by measuring the sensors embedded in the winding. And let's just say the motor winding is 22 degrees Celsius. Okay, that's not the ambient temperature, it's the temperature of the winding. If the motor's been running an hour earlier, it will be much hotter than ambient. Ideally, put in a temperature, because the temperature of the winding affects the megohm value greatly. So the higher the temperature, the lower the megohms. So what we want to do is measure the copper temperature with a handheld gun or by measuring the sensors embedded in the winding. And let's just say the motor winding is 22 degrees Celsius. Okay, that's not the ambient temperature, it's the temperature of the winding. If the motor's been running an hour earlier, it will be much hotter than ambient, particularly in the UK. Maybe in Egypt or Middle East or Far East, it may not be, but we need to really measure the winding temperature rather than guessing. For every 10 degrees Celsius increase in temperature, the megohm value halves. So if you guess and you're 10 degrees out, you could have half the value of megohms that you think, or you could have actually double. Half again, not double. Okay, so we're ready to run a test. We have to press and hold the push the test button, and then if you look on the right, you can just see the red LEDs. Let's just go back a bit with the, there you go. So the red LEDs tell us which leads are live at any given moment. So all 3 leads are live when you do the DC tests. If I have to keep holding this button, but if I press the lock PTT button here until it turns yellow, I can now release this button and the test carries on running, which is very good when you're doing a PI test for 10 minutes, for example. Okay, so we've got voltage, leakage current in microamps, and calculated megohms. So now what I need to do is ramp up my voltage to my megohm voltage, which I'm going to use 500. Okay, 500 volts. When we reach our target voltage, we should press this button here, megohm, until it turns yellow, and that will start a timer for 60 seconds. The touch screen is a little bit sensitive, or maybe not as sensitive as you think even. You have to press it more deliberately. It's not like a keyboard where you can touch it and type very quickly. You have to be a bit more deliberate with your touch. Okay, so we've got 40 seconds left. We've got 500 volts, 0.16 microamps of leakage. Ohm's law calculation gives us 3 gigohms and climbing. The current is very low, so we actually can't see it on the screen. But if we press I-, we can change the scale until we see the current trace. There you go. So red is current, blue is voltage. 10 seconds left. We're going to do a step voltage test next, up to 2000 volts over 5 steps. So you need to calculate what the step increment is. So 2000 volts less 500. Okay, and we're ready now to go to 2000 volts, which is our target. And what we tend to do when we reach target, instead of pressing step, we press high pot. And what that will do, it will actually put in the megohm value here as a obvious value. We would see it anyway, even if we press step, so you can choose, but many people use high pot just for the final step. Okay, so that's the end of the step voltage test. It says complete. So as I said, we can press this button here, lock. That will stop the test. That's discharging the winding. Bigger motors will take longer. And we're now ready to move to the surge test. Now we should save the data. If you forget, it's not a problem. So if I press the surge icon, because I've forgotten to save, it will remind me, you have unsaved data, do you want to save? Yes. Active folder and record? Yes. Okay, so this is the surge screen. We're using the DX. It's a 3-phase test and it defaults to lead number 1. We don't need to change the lead connection on the stator. For this you have to press and hold the button continuously, and then we have to raise our voltage. Now the waveform, we haven't got many cycles on the screen, so we need to adjust the waveform to have more cycles, probably there, and now we can raise the voltage. So raise it continuously, keep the button completely over. The voltage is raising at a relatively slow pace, which is good, and we keep it going until 2000 volts. So just keep the button held on the left and just turn the voltage knob on the right. So we're nearly there, and you let go just before. That's fine, 2030 volts. We've got our surge waveform and our pulse-to-pulse software here. That looks good. Release the button, and that's now captured phase 1. We now select phase 2, and you do exactly the same thing. Press and hold the button, increase the voltage to 2000, and if the winding is symmetrically wound, you should get 2 waveforms that are identical to one another, or very, very close anyway, assuming that there's no insulation weakness or short circuits. 2030 volts, and you can see here a spike. That's actually weak insulation on my stator. Can you see the waveform just moving a little bit left and right? That's arcing between turns. If I get my video camera, you can actually see it. Hopefully. Yeah, there you go. Stops now. There you go. Just in the middle of the shot. That's weak insulation between turns. The only test that can find that is the surge test. Megohm, resistance, inductance will never find it. This is what you need to show your customers. Okay, so that test is finished. You wouldn't normally leave it on as long, but that was a good thing to show you. Okay, so this is clearly showing a problem with phase 2. We do the same with phase 3. Press and hold the button. Notice there's only one red LED on. So lead 3 is live, the other 2 leads are ground. So that's how the surge test works. One of the phases is live, being applied with voltage, the other 2 are grounded, and the relay inside switches with the leads. Ramp our voltage up to 2000. We have a fast and slow ramp here. You can also change how fast they and how slow they are in settings. I wouldn't have it too fast because otherwise you find it difficult to set the exact voltage. Okay, 2030 volts, wait a couple of seconds and then release. So that's the end of the test, but we want to review the data, so we need to save. Active folder record, yes. And now we've captured that information. To review the data that we've stored, we click on this icon. We make sure we've got the right folder and record selected. So actually we want to be 987, don't we? And it tells you here you've got one RLC test, one DC and one surge test. And then we click on this icon here to view. And okay, it defaults to surge for some reason. If we press on RLC, so don't press the bottom row, just press the top row buttons. So RLC, we can now see we've got phase-to-phase resistance and percentage unbalance, phase-to-phase inductance and the unbalance. We've also got impedance and phase angle. Okay, so everything looks good. We've got a very close balance. There's no signs for a problem there. Now we go to the DC icon. Okay, so that's our megohm test and our step voltage. So this is megohm. Then we've got step 1, step 2, step 3, step 4, step 5, and the current is increasing each step accordingly. It looks more or less linear, maybe slightly curved, but there's no significant jump. And we can see here the IR value at 500 volts is 3 gigohms at 22 degrees, and at 40 degrees it's only 888 megohms. That's the difference that temperature makes. At 2000 volts we've got 4.2 gigaohms, and at 40 degrees we've got 1.2 gigaohms. So again, pretty good values, we would be happy with that. And then we've got surge. Okay, we can see our 3 waveforms are more or less superimposed. Here we've got the 3 voltages we've used, so each phase has seen 2030 volts. The values here, 1 to 2, 2 to 3, 3 to 1, that's what we call line to line, EAR, error area ratio. Line to line means we're comparing the waveforms to each other. So between phase 1 and 2 we've got 0% difference, so the 2 waveforms are no difference at all. Between phase 2 and 3 there's a 3% difference, and between 3 and 1 there's a 4% difference, which actually is quite close, so that shows us everything's okay. When we look at the pulse graph, here's where we see the good information. You can see at the beginning red, green and blue waveforms or traces are very similar, but then suddenly here, blue, there's a lot of spiking. The spiking is showing us that the waveform is moving. So there's a change in inductance as the voltage jumps across the weak area of insulation. That effectively changes the number of turns momentarily. That changes the inductance, and therefore the waveform jumps to the left. The spike signifies the jump in the waveform. So whenever you see that, it's very likely to be weak insulation inside the motor. And we know it's only on the blue phase. But if you look up here, blue is lead 2. You can then identify which phase of the motor has the problem. Be aware that a bad connection at the clips where you connect to the motor can cause arcing, and it can cause a pulse-to-pulse spike. And if the motor is assembled on site and you're testing a fan, if there is a draft turning the fan slowly, that would also change the inductance as it goes, so be careful about that. Yep, that's about it for the testing. Some of the settings, we can press on settings screen here. It tells us the serial number, the software or firmware version, the calibration dates. My tester is out of calibration, don't tell anybody. And a few things like that. We can go into maintenance mode, so we press maint mode, enable, we type in the password, which is Baker, done, and now we've got user settings. So the user settings allow us to change things like ramp rate. So on my tester, the ramp rates I use are 30 and 90. They're quite good rates. I would recommend you use something similar. When they come from the factory, the testers are set at a higher level, and I think they're too high. So that's my recommendation. Then you've got the DC times. So DC high pot or step is 60 seconds per step. If that's deemed a bit long by the customer, you could come into this one here, times and limits, DC test times, step or high pot, and I'm going to say 30 seconds, done. So now you can see the high pot step or step voltage steps are 30 seconds only. What else should I show you? EAR fail stop enabled means that if on the pulse to pulse software one of the spikes exceeds the set tolerance, which in this case is 10%, that's the dotted line, the test will stop. So that tells us we've got weak insulation and we've stopped the test. Line to line EAR is 5%, so for a symmetrical winding generally they are less than 5%. Some people would set that to 10 though. But you're basically looking at how separated the waveforms are. If you test a 2-pole motor or a 3-tier winding, they are naturally unbalanced by design. So the inductance values are not balanced even when the motor's good. So you will see an unbalance during the surge test and during the inductance test. If you have the rotor present in the stator when you're doing the test, you will also see an influence from from the rotor on the stator inductance. So again, you're very likely to see unbalanced surge and unbalanced inductance. If you turn the rotor during the test, you'll see the waveforms move or the inductance values change. Okay, you can change the time and date. When the tester arrives from America, it will be on American time, so you would need to do that. It's fairly logical. And when you've made any changes that you want to make, you press return, and you must press save changes, otherwise you'll lose the changes. Okay, so now we've captured those changes.
My name's Paul Knott.